Hi there and welcome back to the College Physics series. In today's video, we're going to be solving projectile motion problems. So download the guided notes that are in the description and follow along with me. Thank you for being here. Let's get started. Before we solve projectile motion problems, let's quickly review the key concepts you need to fully understand. Here I've drawn a Venn diagram that illustrates the similarities and the differences between the horizontal and the vertical motions of a projectile. Let's begin with the vertical motion because there is a key concept I forgot to mention, and that's the one here with the asterisk. That key idea is that the time to go up is equal to the time to go down. If this is the floor and this is the path of my projectile, what this idea says is that if I draw a line at the peak, this means that from t equals 0, from the very beginning, let's say the ending takes a total 1 second. So from beginning to end, it takes a total 1 second. That means at the very peak, this is half a second. So it takes half a second for it to rise up and then half a second for it to come down. Those time intervals are equal. So if I have another path, from beginning to end, it takes 5 seconds. That means I know that at the peak, it takes 2.5 seconds later from the beginning to arrive at the peak. And we're going to be utilizing this concept in the examples we have today. Moving on, in the vertical motion, it is accelerated motion, where the acceleration is equal to negative g. In the vertical motion of a projectile, the velocity changes over time. When it rises up, when it's moving upward, it is slowing down. And when it's falling down, it is speeding up. The motion in the vertical direction is described by this kinematic equation. The vertical motion of a projectile is dependent on gravitational acceleration. This means that the value of g can be different on whatever planet that you're on. So if you were to conduct an experiment here on Earth and you got a time of flight total to be 1 second as we got up here, then on the moon, these values are going to be different because the value of g on the moon is very different. Lastly, for the vertical motion, the velocity reaches 0 at the peak, right where it changes direction. So those are all the important ideas that you need to understand about the vertical motion of a projectile. Now for the horizontal motion of a projectile has constant velocity, which means that it has 0 acceleration. It stays the same the entire time that the projectile is in the air. Well, independent of mass is actually something that belongs to both. So let's put it where it belongs. The horizontal motion is described by this equation of uniform motion. The horizontal motion continues indefinitely if there is no ground. So if you set something off an edge and there is no ground, then this horizontal motion is going to continue until there's something that stops it. Finally, the horizontal motion of a projectile is affected only by the initial velocity in the horizontal direction. Now here's what the horizontal and vertical motions have in common. They occur simultaneously. They happen at the exact same time. The key variable that acts as the bridge between these two motions is delta t, the time. Although each of these equations are different here, what they do have in common is the delta t, the time interval. That is what is the same between these two motions. And whenever you're solving problems and you need some link between the horizontal and the vertical, the time interval is always going to act as your link. So the time of flight, delta t, is the same for both motions. Both the horizontal and vertical motions are influenced by the initial launch conditions. As an example, if I change the angle, say from here to maybe this one, let's say 2 theta. If I double the angle, that's going to affect my horizontal and my vertical initial velocities. I can also affect it by increasing the magnitude of the velocity or decreasing the magnitude of the velocity. Next, my correction, both motions are independent of the mass of the object. And lastly, both motions are completely independent of one another. And this summarizes all of the key ideas that you need to completely understand, so that way you have no issues solving projectile motion problems. So let's begin with our first example. So let's go ahead and read our first example. It reads, you are playing with a friend and decide to pass the ball to them. You throw the ball with an initial speed of 15 meters per second at an angle of 45 degrees above the horizontal. Your friend is standing 12 meters away from you. And here we have 3 questions. 1 is, how long will it take the ball to reach your friend? 2 is, what is the maximum height the basketball will reach? And 3 is, will the ball travel far enough to reach your friend? The best first step is to always draw a picture. So let's imagine this scenario. So let's imagine we are here and we're tossing this basketball to a friend. So this is where we're at. So this is the starting point of the motion. We know that this basketball is going to be launched at a speed of 15 meters per second at an angle that is 45 degrees above the horizontal. So since this is the starting point, this is where I'm going to find information about the initial vertical position, the initial time, the initial horizontal velocity, the initial vertical velocity, and the initial horizontal position. Notice how there's a lot more variables here compared to a simple one-dimensional kinematic problem. Well, this is because we're moving in 2 dimensions at the same time. We know that our friend is 12 meters away, but we can't necessarily assume that the ball's going to land there. That's what we're trying to figure out. So with this in mind, let's go ahead and create our knowns and unknowns. Since this object is being tossed in the air, I know that vertically, my acceleration is just minus g. Because this object is thrown, it has an initial velocity in both the vertical and the horizontal. We can figure out the initial velocities in the horizontal and the vertical by finding the components of the velocity. So the initial velocity initially is going to be the magnitude times the sine of theta. It's times the sine because the right angle is towards the left. So this is going to be 15 meters per second times the sine of 45. And that's going to give me an initial vertical velocity of 10.6 meters per second. Therefore, over here I can write that the initial vertical velocity, 10.6 meters per second. I also have an initial horizontal velocity. I can find that by taking the magnitude multiplied by the cosine of the angle. So I'm going to get 15 meters per second multiplied by the cosine of 45. And that is going to give me also 10.6 meters per second. So I'm going to write that here in my knowns. My initial horizontal velocity is 10.6 meters per second. I know that as this basketball moves through the air, it's going to follow an arc, which means it's going to arrive to a peak, which I know that at the very top, my peak is 0. And I'm going to take advantage of that fact in just a moment. Let's identify any other key information in the word problem. I know the initial speed, which I've already accounted for. I know the angle. I've already taken that into account. And we know that this friend's standing 12 meters away. It's not necessarily a known quantity because we're going to figure out how far this ball travels and we're going to compare it to 12 meters to see if it's less than 12 meters, the ball was not thrown fast enough. If the ball lands a distance greater than 12 meters, then we know it was thrown too hard. Or if it was thrown exactly 12 meters, then the ball perfectly reaches our friend. Looking at our questions, how long will it take the ball to reach your friend? This is a question of time. So I'm looking for the time. What is the maximum height the basketball will reach? I'm looking for my final vertical position. Third question, will the ball travel far enough to reach your friend? So that is asking for the displacement, which we're also going to call our range, the range of this projectile, which we will talk about a little bit later in this video. So let's first start off with the time of flight question. In order to tackle the time of flight question, I'm going to take advantage of a few concepts. I'm going to purposely choose the peak to be my end. So the starting point is going to be where it starts, and I'm going to purposefully stop the motion. I'm going to stop my analysis at the very peak because I know that the final vertical velocity, so it's VYF, is equal to 0. And I get to call it F because I'm deciding that that's the end of my analysis. What I can also take advantage of is to solve for the time it takes to reach the peak, because I can take advantage of the concept that the time to go up is equal to the time to go down. So if I find the time interval to go from here to here, then I can just double it and get the total time of flight. And that's going to be my first step to answer this question. So the VYF is going to be 0 meters per second because I decide that that's my stopping point for my analysis of the motion. So to answer the first question, I'm going to choose this equation. My final velocity equals to my initial velocity minus the acceleration times the change in time. I'm going to choose this because I know that my final velocity at the peak is 0 and I can solve for this time of flight. So the equation I get is 0 equals to the initial velocity minus g delta t. But I'm going to go ahead and add g delta t over to both sides to isolate the VI, to isolate the VYI. So I'm going to get g times delta t is equal to the initial velocity. To finally solve for this time interval, I'm going to divide by g, and that's going to give me that the time of flight to hit the peak is going to be my initial velocity divided by the magnitude of freefall. Well, this is easy for me to figure out because I know the initial vertical velocity is 10.6 meters per second, and I just have to divide that by 9.8 meters per second squared. This is going to give me a time of flight of about 1.08 seconds. So this represents just to get to the peak. So the total time of flight is going to equal to 1.08 seconds times 2 to complete the entire motion, which is going to give us 2.16 seconds. So in my knowns, I can now write that the time of flight is going to be a total of 2.16 seconds. 2.16 seconds represents the amount of time it takes for this projectile to reach its lowest point. Once again, let's go ahead and answer the question about the range, about how far this projectile is displaced. And this will answer question 3. So this is the next easiest question because the horizontal motion is just described by one equation. The final horizontal position equals the initial horizontal position plus the initial velocity times the time interval. In this case, this delta t is the time of flight. Well, I'm going to decide that where it begins horizontally is 0. It's going to start from 0. So therefore, my equation is going to simplify to be this final position, which we're going to call the range. That's equal to the initial velocity times the time of flight. So the range for this projectile is going to be 10.6 meters per second multiplied by 2.16 seconds. And that's going to be 22.9 meters. How does this compare to the 12 meters that our friend is away? Well, this means that we're going to overshoot our friend by quite a bit. This means that the projectile was thrown too far. So now we know that this range is 22.9 meters. Lastly, let's answer the second question. What is the maximum height the baseball will reach? So to answer question number 2, you need to think back to which equations are going to help us out the most. And for number 2, it'll be this equation. So number 2 is asking for the total height reached by this projectile, so my final vertical position. I'm going to say that my initial vertical position is 0. So wherever it's thrown from, that's my starting point. I know this is the first thing we calculated. I know the time of flight, and I know the delta t here, and I know the magnitude of acceleration. You need to be very careful because the delta t is not the total time of flight, because we want to know when it reaches this peak, this highest end. And it reaches the peak at half of 2.16, and that occurred at 1.08 seconds. And so that's going to be the time that I use in that equation. So we need to be very careful. So my final vertical position is going to equal to 10.6 meters per second, my initial velocity, times 1.08 seconds, my delta t, minus half of 9.8 meters per second squared, that is my g, multiplied by that time squared. So there's everything plugged in straight from our knowns and unknowns. Leaving this for the calculator, we're going to get 5.7 meters. And that is going to complete all 3 questions for example number 1. The main idea here is that you need to carefully be monitoring the concepts that you are applying to answer each question. The mathematical part of answering these questions is the exact same as freefall questions or the exact same as uniform motion questions. You need to be completely aware of the concepts you are applying, and you need to be aware of whether the concepts are valid. For example, if I did not use the 1.08 seconds in my last calculation and instead used the 2.16 for the total time of flight, that would be an invalid use of the time of flight concept. If I had used the 2.16 seconds, I would be calculating the height at the very end of the motion. I hope this process has been clear, and I hope that I have explained my problem-solving process clearly enough for you to understand. Let's go ahead and do another example. So here we have example number 2. In a dock jumping contest, a dog runs straight off a dock with an initial speed of 6 meters per second. The dock is 1 meter above the ground. And here we have 2 questions. The first one reads, how long will the dog take to reach the water? And number 2 reads, how far will the dog travel horizontally before hitting the water? Like we did in the previous problem, let's go ahead and understand what's going on by drawing a picture. So here we have a dog, and this dog is going to be running straight off. Whenever it says straight off, that means that the motion is completely horizontal. So I'm going to have an initial horizontal velocity of 6 meters per second. And I know that the dock is 1 meter above the ground. So the dog is going to follow a path that acts like this, and it's going to reach the water. The question is, from here to here, what is that range? Or how far does the dog travel? And then also, how much time does it take to hit the water? So here's my starting point, and obviously the water is my ending point. At my starting point where the dog is at, this is where I'm going to find my initial horizontal position, my initial vertical position, my initial vertical velocity, my initial horizontal velocity, and my initial time. At the very end, that's where I'm going to find my final vertical position, my final horizontal position, which we also call my range, the final time, my final vertical velocity as well. So let's go ahead and identify our knowns and unknowns in this problem. The first question reads, how long will the dog take to reach the water? That is a question of time. So I'm looking for the time of flight in this case. I'm also being asked how far the dog is going to travel. So I'm looking for the range. So because this dog is running straight off, it has an initial horizontal velocity of 6 meters per second. That means if it's completely horizontal initially, I have 0 in the vertical. And that's going to be great for us because zeros simplify equations amazingly. Since this dog is falling in the air, its vertical motion is experiencing free fall. So the vertical acceleration of the dog is negative g. I know that initially the dog is 1 meter above the water. And when it reaches the water, the final position is 0 meters. So to get the time of flight, I'm going to use this equation. Luckily for me, I know that the final vertical position is 0 and that the initial velocity is 0, which is going to cancel out this entire term. As a result, this is what my equation will look like. I get 0 equals to the initial velocity minus 1/2 g delta t squared. I'm going to add this 1/2 g delta t squared to both sides to make everything positive and then simplify and solve for delta t. On the right hand side, I'm going to get 1/2 g delta t squared equals to yi. What I'll do is I'm going to multiply by 2 on both sides in order to cancel out this 1/2, and I'm going to get that g delta t squared equals 2yi. Next, I'm going to divide by g to cancel out the g on the left hand side. So I'm going to get that my delta t squared is equal to 2yi divided by g. Finally, to solve for delta t, I'm going to be taking the positive root on both sides. And we'll do this up here. That's going to give me that this time interval is going to be the positive root of 2 times the initial vertical position divided by g. Now, I'm deciding not to use the negative root because I have no use for negative time. So to solve, it's going to be the square root of 2 times 1 meter divided by 9.8 meters per second squared. Therefore, the amount of time that it takes for this dog to fall is 0.45 seconds. That is the time interval for this projectile. And that answers question number 1. Question number 2 is how far will the dog travel horizontally before hitting the water? Now that I know this time interval, question 2 becomes a breeze. The only equation in the horizontal direction is the final position equals initial position plus the initial horizontal velocity times this time interval, the time of flight. Remember, my final position I'm calling my range. And what is the initial position? Well, I can define that to be 0, starting point. So this is going to cancel. It's equal to my initial horizontal velocity, 6 meters per second, multiplied by this time of flight that I just calculated, 0.45. Therefore, the range that this projectile will reach is 2.7 meters. And that will complete example number 2. Now let's explore what is called the range equation. The range equation is a shortcut equation if you know the angle at which a projectile is launched at and if you know the initial speed of the projectile. This is the range equation. The range is equal to the initial velocity squared times the sine of 2 times the angle divided by g. So all that you need to know is the speed at which it is launched off horizontally, the angle at which it is launched at. Plug it into this equation and you'll automatically get the range of a projectile. Now this equation is only valid for projectiles that start and end at the same height. So let's go ahead and derive this equation so that way I can show you where this comes from. Let's say we have this projectile where this is where it starts, where this is the starting point, and this is where I'll find the initial vertical position, the initial horizontal position, the initial time, the initial vertical velocity, and the initial horizontal velocity. And this will be the ending point for this projectile. And I'm going to find all the same things but final. XF, YF, TF, VYF, and not any final horizontal velocity because that's constant. So if I were to do some knowns and unknowns, what I'm looking for is the range. I want an expression for the range. Since it starts and ends at the exact same height, I know that my displacement is equal to 0. My acceleration is minus g. So the initial velocities are going to be any value that we're going to call vi and at any angle. So the vertical velocity initially is just going to be v sine theta we'll call it VI sine theta. And the initial horizontal velocity is going to be VI cosine theta. Here's what I know about the range equation. For me to find the range, I just need to multiply my initial velocity horizontally times the time of flight, the delta t. But I don't know what delta t is. Well, what I'm going to do is that I'm going to use the vertical information to find an expression for delta t and then plug it right in. Now, just as a side note, this is the equation we use for horizontal, but I'm assuming that it begins horizontally at 0 meters. And then this final position becomes range, and then that's where I get my initial horizontal velocity times delta t. So I skipped that step, but I guess I explained it now. So let's go ahead and use some of the vertical information to develop an expression for delta t. And I'm going to use this one. Now, lucky for me, I know that my initial vertical position is 0 and my final vertical position is also 0 because it reaches the same height at the very end. Therefore, I can rewrite this equation with these simplifications. Now, I actually know what my vertical velocity is. It's just the total speed that is launched at times the sine of theta multiplied by delta t minus 1/2 g delta t squared. Well, I need to solve for time, and this is a quadratic. I can simplify this for us just by dividing a delta t on all sections of this equation. So that it cancels here, I cancel out an exponent, and on the left-hand side, I still get 0. So what I'm going to get now is that I get my initial velocity times sine theta minus 1/2 g times delta t. Performing all the math steps, I'm going to get an expression for delta t to be 2 vi sine theta divided by g. And this is what I'm going to plug in to my range equation over here. And I'm going to develop this range equation that I gave you at the beginning. So my range is equal to the initial horizontal velocity. Well, I know that that is VI cosine theta. And I'm multiplying this by delta t. That is 2 VI sine theta over g. So let's multiply these out. I'm going to bring let's bring the VI squared up front, multiplied by 2 sine theta cosine theta, all divided by g. Well, this part right here, 2 sine theta cosine theta, can be simplified using an identity. That is vi squared times the sine of 2 theta, all divided by g. And that is where the range equation comes from. All that you need to know is the initial speed at which the projectile is launched and the angle at which it is launched at. And this formula will output the range that a projectile reaches. Remember, this equation is only valid if the initial vertical position and the final vertical positions are the same. If somehow the projectile ended on some ledge, this equation would not work. Because what this equation requires is this. The final and the initial velocities must cancel, must be 0. That's what this expression depends on when I plugged in my delta t. So just be aware of the validity of this equation. Now let's go ahead and talk about complementary angles. Interestingly, two launch angles that add up to 90 degrees yield the same range. For example, if I have a 30-degree launch angle, if this represents a 30-degree launch angle, well, what number do I add to give me 90? Well, a 60-degree launch angle. 60 plus 30 is 90. So if I launch the angle at 60 degrees, I'm going to find that it's going to give me the exact same range. And that's an interesting pattern that the real world has. So if I have two angles that add up to 90, their ranges are going to be completely identical. So I could do, another option is, let's do 10 degrees. So this would be a 10-degree angle, and let's do 80 degrees. Extremely, extremely high. Those two angles are going to have the exact same range. One last idea is that if you want to choose an angle for maximum range, if you want your projectile to have as maximum a range as possible, you're going to set your angle to 45 degrees. And the reason why that is because in this equation, we have sine of 2 theta in our range equation. Sine of 2 theta. Well, the sine of a certain input is a maximum when it equals to 1. Well, we find that maximum when the input is 90, because the sine of 90 is 1. So the angle that produces that maximum, when you divide it by 2, that angle is going to be 45 degrees. So when I plug in 45 degrees, I double it, it gives me 90, and the sine of 90 is a maximum of 1. By understanding these patterns, you can predict and solve a wide variety of projectile motion problems. Let's go ahead and end with a try-it-yourself problem. So here are the paths of two different balls. This is path number 2, and this is path number 1. The question is, which ball is in the air for a longer time. And that is going to wrap up our lesson today on solving projectile motion problems. Please remember to keep the key concepts in mind whenever you are in the middle of the problem-solving process. It's a lot to juggle around in your head, so it's very, very easy to become confused and make mistakes. If you found this video to be helpful, please consider subscribing, liking the video, and sharing it with others who might find it useful. Thank you for being a part of the College Physics series. I will see you in the next lesson.